Good morning, everyone. I'm Daeho Jeong, currently working at Samsung Electronics in Korea, and all of the authors are affiliated with Sungkyunkwan University in Korea. The topic of this talk is how to improve the overall responsiveness of modern-day mobile devices under intensive I/O pressure. Let's start with showing you a simple multitasking scenario for an Android phone. A user is copying a large size of file and presses the home button to return back to the home screen. Now he can perform another job while copying the file. And then our user touches the Contacts apps icon to find his friend's email address. But his smartphone doesn't respond to his request for a long time, and he'll finally get upset. Eventually, the Contacts app's UI shows up. However, by our measurement, the Contacts app start time is gradually increased with lots of variation. So where does this kind of delay come from? Is this delay caused by a shortage of CPU resources? No, we have sufficient numbers of CPU cores for performing these two jobs simultaneously. Is this related to memory shortages? No, the delay from the page reclaim is insignificant in this case. Through our extensive investigation, we found that most of file system cores of the Contacts app experience a large amount of unexpected delay under heavy I/O pressure. And surprisingly, the root cause of this delay turned out to be an asynchronous I/O, not even synchronous I/O. We chose to call this asynchronous I/O Quasi-Asynchronous IO. Before introducing this kind of I/O, I want to remind you about the existing I/O scheduling policy in Linux kernel. Basically, Linux classifies all the I/Os into sync or async I/O. Because a task can be blocked waiting for the completion of synchronous I/O, the CFQ I/O scheduler gives a higher priority to synchronous I/O for better responsiveness. The following is how it typically happens in most scenarios. The CFQ I/O scheduler maintains lots of internal queues and gives each queue a limited time slice. But sync queues get larger time slices than async queues, and most asynchronous I/O requests even have to share the smaller time slices. In addition, the CFQ I/O scheduler limits the number of asynchronous requests that can be dispatched depending on the situation. Above all, a newly inserted synchronous I/O can preempt other asynchronous requests. This has worked reasonably well until now, but is this ultimately enough? Our answer is no. Imagine an I/O-intensive situation when one or more tasks are writing large amounts of data asynchronously. The newly generated dirty pages stay in the page cache for a while to maximize the effect of I/O buffering. When the number of dirty pages exceeds the background dirty ratio, most of the dirty pages are flushed out as asynchronous I/O by a K worker as soon as they are made dirty in the page cache. Finally, the request queue is filled up with asynchronous I/Os, and these requests will be processed one by one in the order of increasing sector number to maximize I/O throughput. So, where does our quasi-asynchronous I/O come into play? In spite of the nature of asynchronous I/Os, which any task wouldn't wait for its completion, what if a task is waiting for the completion of the asynchronous I/O in the rest position of the request queue? The asynchronous I/O will delay the execution of tasks like the synchronous I/O does. We define this kind of asynchronous I/O as quasi-asynchronous I/O, QASIO. QASIO is issued asynchronously but should be treated as synchronous I/O, and QASIO can be detected only at runtime, unlike sync and async I/O. Also, it makes the foreground task blocked for an unexpected amount of time, and this problem is similar to the priority inversion problem. This is the definition of QASIO. So up to this point, I have introduced a new type of I/O. From here, I will explain how a task can have dependency on QASIO and how severe the delay by the dependencies is. Towards the end, I will demonstrate our solutions overview and finally the evaluation results. Now you know what QASIO is. And then you may want to know the answer to how can a task have dependency on QASIO. This is one of the most important parts of our work, and we found the answer by the thorough exploration of Linux source codes and lots of profiling. We found that each task can have direct or even an indirect dependency on QASIOs. We have also publicized all the different types of QASIO dependencies. There are 4 direct dependencies and 2 indirect dependencies. Because we have limited time today, please refer to our paper for the details of all types of dependency. Here I will explain some of them with detailed use cases. The first use case is concerned with starting apps or interacting with the app's UI. When an app's UI shows up or a user interacts with the UI screen in the Android platform, the app invokes several file system calls to update each stage saved in SQLite databases or XML file. I will explain the delay which an app experiences in a single file system call under intensive I/O workload. First, a bulky I/O task, which is copying a large file or downloading lots of data through fast connectivity, makes numerous dirty pages. And a K-worker thread wakes up in order to prevent memory from being occupied by too many dirty pages and pushes out those dirty pages as asynchronous I/O requests. The request queue will be full of these asynchronous I/Os. And a metadata buffer, which was modified in the previous run, is changed into a dirty state in order to be checkpointed after each journal commit. It has one of the metadata listed on the screen. This metadata buffer is also flushed out immediately and locked by K-worker. When a user launches an app like Context, the app is accompanied by a series of file system calls. Finally, the app invokes several file system calls before showing its UI. The invoked file system calls will attempt to modify the metadata buffer, which is being written back. So it will fail and be put in wait state. We call this kind of dependency D-meta dependency. Next, I want to introduce another direct dependency related to Fsync, which is frequently used in the Android platform. Normally, when you use a Fsync system call, you have to write data to be synced using a write system call in advance to Fsync system call. And by invoking Fsync system call, dirty pages written from the previous write system call will be flushed out as synchronous I/O. In this case, the I/O will be processed with a higher priority than other asynchronous I/Os. Normally, this is what we expect from any Fsync operation. However, what happens to Fsync operation under intensive I/O pressure? Here is the same precondition. As you can imagine, a UI task uses a write system call in order to recode its own data, but the dirty pages of the task are immediately flushed out as asynchronous I/O by K-worker under heavy I/O load. The task invokes Fsync to flush out the buffered data as synchronous I/O, but all the data was already flushed out through asynchronous I/O. And the task should wait until the completion of all the I/Os of not only the file's data, but also most of the I/O that are queued up in the request queue. We call this dependency Desync dependency. Unlike what we expected from Fsync, when a large file is being written in the background, the Desync dependency causes a large amount of delay of Fsync. Lastly, this is a more complex use case representing an indirect QASIO dependency. We start with a similar precondition. Let's say task A writes data in 1 kilobyte size. This is a partial page write. This partially written page is also driven out from the memory when the I/O pressure builds up intensely. Our task A tries to write in the remaining part of the page once again. Before that, it obtains a journal handle of running transaction for the metadata modification after the data writing. Finally, the task tries to copy its data to the page but the page is on the write back, and the task needs to wait for the completion of the I/O. This is a data dependency, and this affects other task execution in an indirect way. After a certain period of time, the running transactions start to be committed, and the transaction will be locked because a handle is still opened by the task A. Under this condition, all the other tasks cannot obtain a new journal handle because the running transaction is locked. It means that all the file system calls cannot proceed anymore, and this QASIO dependency broadly affects the system. We call this kind of dependency IJ handle dependency. Of course, the latest disabling stable page patch allows data pages to be updated while they are under the write-back situation and eliminates the data dependency. But this can be unacceptable again in future mobile devices because the hardware-supported encryption of I/O is seriously being considered as a way of performance optimization. The next question is how severe is the delay caused by QASIO? It depends on how many requests are ahead of QASIO in the request queue. The number of outstanding requests for mobile devices is expected to only rise and stay that way in the future because the connectivity speed will continue to increase and smartphone will process many jobs simultaneously with multitasking, even multi-window mode. Aside from that, the underlying storage device's I/O performance has to be also considered when estimating the worst-case QASIO's delay. On one of the latest smartphones, Samsung Galaxy S5, the worst-case latency of a single file system call by QASIO takes over 1 whole second. The slower the I/O performance is, the longer the worst-case delay is. On a product using slower TLC-based eMMC, the worst-case latency even takes more than 4 seconds. We also expect the I/O performance of mobile devices can be more degraded as using TLC-based eMMC for the low cost. So the QASIO's delay will be getting worse as well. These figures show that how much degraded real-life scenarios are by the QASIO's delay. The right sidebar on each figure represents the app performance under intensive I/O workload. As you can see, all the performance are adversely affected, and most of the degradations are from the QASIO's delay. The context app start time is slowed down by a factor of 2.4 in the worst case. The biggest part of the worst case app start time is derived by over 1 second of the QASIO's delay. You can also see the severe variation of the app start time. This kind of fluctuation in performance will be noticed by the users who will definitely not appreciate it at all. The second figure is about the continuous high-speed shooting mode in the camera. The shot count is also decreased by 19%. In the final figure, Angry Birds app install time, excluding app downloading time over the network, is increased by 35%. And then, how can you reduce the QASIO's delay? Our solution is boosting QASIOs. How can you boost QASIOs? We focus on only direct dependency, not indirect dependencies, because if we leave the problem from direct dependencies, the problem related to indirect dependency will be automatically taken care of. Finally, we define 2 requirements to boost the QASIO. First, if a task is blocked waiting for the completion of an asynchronous I/O, the I/O is definitely QASIO. So the information about the QASIO should be transferred to the I/O scheduler. Second, the I/O scheduler should prioritize a QASIO and its own queues based on the received information. The first requirement is for BFS-MM, the specific file system like ext4, and the block layer. And it should be implemented across these layers. The second requirement should be properly implemented in each I/O scheduler, and we selected the CFQ I/O scheduler for our pilot solution. This is our implementation overview. We found all the functions waiting for an I/O to be completed in the kernel and added some QASIO detection algorithm in there. The key of this algorithm is that it first checks whether the buffer head or the page is submitted as asynchronous IO, and if the IO is identified as asynchronous IO, it extracts the sector number from that and sends the sector number to the IO scheduler through the block layer. And then the IO scheduler will search the IO involving the sector number. Actually, all the asynchronous IOs in Linux kernel are flushed out by kworker only. So the CFQ IO scheduler gathers all the asynchronous IOs into a single internal queue. In that queue, all the IOs are managed in the red block tree data structure. So we traverse the red block tree and look for the IO request, which includes the received sector number. And if the request is found, it will be inserted into the QASIO list. Finally, whenever an asynchronous CFQ is selected for dispatching a request, we check the QASIO list first and then dispatch QASIO requests, if any. You can also refer to our paper for more detailed description about our solution and corner cases. So how much improvement does our solution bring to the file system call latency? This is our test environment, and we evaluated using 3 different test methods: in-house micro benchmarks, real-life scenarios, and well-known Android I/O benchmarks. We made 5 benchmarks with different combinations of file system calls frequently used in the Android platform. For example, the M1 benchmark iterates the test 500 times. In each iteration, M1 opens the same file with create system call and then writes 4 kilobytes of data to the file. Finally, it performs Fsync and closes the file. Note that this micro benchmark mimics the I/O patterns of the SQLite database system. We executed all the benchmarks for lots of iteration under heavy I/O pressure. As you can see, the total elapsed time of each test is gradually reduced up to 83.1%. The reason for this improvement is that the worst-case latency of each file system call is drastically reduced by our solution. In real-time scenarios, the context FSR time is reduced by up to 44.8% and returned close to the FSR time without heavy I/O workload. The waiting times in kernel waiting functions for demeta and discard are reduced by 96.1% and 87.4%. Let's look at the burst shot performance in the camera app. The shot count is also improved by 14.4%, and the most of improvement is achieved by the reduction of total wait time of D data. The Angry Birds install time is also improved by 11.5%. Finally, for the Android I/O benchmarks, AnTuTu and RLBench, all the scores are also suffering under intensive I/O pressure. But with our solution, the 2 scores are recovered by 10.2% and 17.1%. An interesting observation is that boosting QASIOs improves the performance of AnTuTu by about 12%, even when there is no asynchronous IOs in the background. This means AnTuTu itself issues plenty of asynchronous IOs, and its performance was already being affected by QASIOs. In conclusion, we introduced a new type of I/O, QASIO, and our novel scheme to detect and boost QASIOs for minimizing file system calls latency. In our evaluation, the worst-case latency of a file system call and worst-case FSR time are improved. For future work, we are planning to continue investigating on other types of systems, including server environments and low-end mobile systems. We will further fine-tune our solution, separately optimized for each QASIO dependency type. Thank you for your time today. If you have any question, please ask. Thank you.
Any questions? Hi, this is Amit Good from Tintri. So, did you have a chance to compare the optimization that you have with something like all the async IO have the same priority as the sync IO? What would that look like?
Excuse me?
So if
You
we
mean-
treat async IO with same priority as the synchronous IO?
Yes. You mean synchronous IO preempt other asynchronous IO?
Yeah, yes, yeah. So how would that look like versus the optimization that you have? Do you have?
What is the difference from that? You
Yes.
mean that? Actually, we defined a new type of IO, QASIO. This is a more urgent IO among the asynchronous IO. So we select the special type of IO from all the asynchronous IO, and then we boost that.
Okay. Okay, maybe I'll take this offline. Thanks.
Thank you.
Do you have any comparison of not using the CFQ IO scheduler and just using the no-op IO scheduler and thus not even introducing the latencies for the async IO that you're mitigating here?
I can hear you.
Is this better?
Oh, yeah.
Okay, so do you have numbers that compare a setup that's not using the CFQ IO scheduler but the no-op one, which basically does not delay IO? Because in that case, the async IOs will not actually get delayed and wouldn't need to be mitigated.
You mean, did I try the other IO scheduler?
Yes, and specifically the no-op one, which does no IO scheduling.
Or something else IO scheduler? I didn't try, but I will try those in the future work.